Hey everybody. All right, so I'm going to be making these videos about the lessons that we learn in class every day. And then I'm going to be posting them on Schoology so that if you have to miss school for whatever reason, if you have to stay home, that you'll have these videos there to refer to and you'll know what you missed that day, and you'll have me kind of explaining the notes so that hopefully you can stay up to date the best you can. Please also remember that you can find my completed version of the notes in the folder on Schoology for that particular chapter. So right now we're on chapter 2. If you look on Schoology, there's a folder that says chapter 2 matrices, and inside that folder is a copy of the blank notes as well as a key to the notes. So you've got all the notes already filled out, and sometimes that might be enough for you to get by on. If not, then you can come here and watch this video. I'm going to post these videos in, so I'll have a folder on Schoology that says remote assignments, and then within that will be a folder for each day of, day that we have class, and inside that folder there'll be a description of what we did that day, and then also any videos that pertain to that day. I'm also going to put these videos in the chapter to which they pertain. So again, in the chapter 2 folder where you find the notes, you'll also find a folder that says videos, and you'll be able to find these videos in there as well. Just trying to make them as available to you as I can. Keep in mind that I'm going to try to keep these videos equivalent to whatever it was that we learned in class that day. However, I don't always know exactly how far we're going to get in class each day. I have a rough idea. I know about where we're going to get to, but I'm not always exactly right about that. So these videos might go a little bit longer than we actually went in class, and it's possible that it might not quite get to everything. And if so, then we'll just have less for you to get caught up on. Or in the next video, maybe I'll start the next video with whatever, that previous video didn't get to, that sort of thing. So I'll try to do the best I can to get everything in the videos, but we're just going to play it by ear and see how it goes. So without further ado, we got Stefan, the math fish, up there. He was begging me not to do another math video, but that's too bad. We are going to move on to chapter 2. So again, if you don't already have your chapter 2 notes, they are available in the Schoology folder that says chapter 2. If you're able to print those off at home, great. Maybe just print off the first few pages. I'll let you know that we would need, not counting the cover sheet, we would need 1, 2, 3, 4, 5, 6 pages of notes, and I'm counting the front side as 1 page and the back side as the second page. 6 pages, that seems like a lot, but these are going to go pretty fast because this is all introduction to matrix stuff. It's all pretty simple. There's a few new, well, it's all new, but most of it's pretty simple. A few things that maybe aren't as simple, but I won't go quite as fast through, okay? So we're going to do this thing. Let's share my other camera here. Hopefully it focuses, and it did. That's awesome. First try focus. That doesn't always happen. Make myself a little bit bigger there, and let's get into this. Okay, so I am, like I said, I am going to be moving pretty fast here, so hopefully this won't take too awfully long. So first of all, a matrix is just an arrangement of numbers in rows and columns. So you can see in this case, I have 2 rows and I have 3 columns. It's important to know that a row is always horizontal and a column is always vertical. So we've got 2 rows and we've got 3 columns, and we can write that over here. When we describe how many rows or columns a matrix has, we call that the dimensions of the matrix, or I might call it the size of the matrix. So I would say that this matrix is a 2 by 3 matrix. That's its dimensions. We always list rows first and columns second. Rows first, columns second. So there are 2 rows and 3 columns in this matrix. Matrices are nothing more than that. It's just an arrangement of numbers in rows and columns. Okay, if we want to discuss or describe just a particular number in the matrix, we call each individual number an element of the matrix or an entry in the matrix. This notation here, the A, just stands for whatever number it is we want to talk about. That number can change, so we use a variable for it. These numbers talk about the row and column that we want to focus on. So A with a subscript of 1, 2 would mean the first row and the second column. So I would look at the first row and the second column. The number that's in the first row and the second column is this 5. So A sub 1, 2 is talking about that number 5. Just like A sub 2, 3 would be second row, third column, and the number in that position is that 7. The number -1, you see that right here, that is in the first row and the third column, so we would call that A with a subscript of 1, 3. First row, third column. Okay, if the number of rows and columns are the same, we call that matrix a square matrix. And square matrices are kind of special, so we want to know when we're dealing with a square matrix. In the example down here below, you can see example B has 3 rows and 3 columns. That is a 3 by 3 matrix. It has the same number of rows and columns, so that is a square matrix. You can see it looks like a square. If the matrix has only 1 row, then it's called a row matrix. You can see example A here just has 1 row. We would actually say that it has 1 row and 4 columns, because you can see vertically 1, 2, 3, 4, but horizontally just 1 row. So that is a 1 by 4 matrix, and that is called a row matrix. If a matrix has only 1 column, it's called a column matrix. And you can see here that example D has just 1 vertical column. It does, however, have 1, 2, 3 rows. There's just a single number in each row. So rows by columns, we would say that that is a 3 by 1 matrix. And again, that's called a column matrix. Example C doesn't fit into any of these descriptions. It just has 3 rows and 2 columns, so we would just call that a 3 by 2 matrix. There's nothing else special about it, though. All right, moving on to the next page, we're going to discuss adding and subtracting matrices. So in example A, you can probably guess how we're going to add these matrices together, and that is that we're just going to add together numbers that are in the same position in each matrix. So this 2 is in the upper left, the 3 is in the upper left. We're going to add the 2 plus 3, and we'll have a 5 in the upper left. The -4 and the 0 are in the upper right. Add them together, we get -4. Bottom left is 5 plus -4, which would give us a 1 in the bottom left. Bottom right is -9 plus 8, which gives us a -1 in the bottom right. For example B, it's exactly the same thing. Just make sure that you're careful about when we're subtracting the matrices instead of adding them. So in the upper left here, we start with a 3 and we subtract a -2. Subtracting a -2 is the same as adding a +2. So 3 minus -2 really means 3 plus 2, which gives us a 5 in the upper left. In the upper right, 4 minus 9 gives me a -5 in the upper right, and so on. I'm not going to finish that one off. Well, I will talk about example C. You'll notice in example C, we can't really match up all of the numbers because they don't have the same dimensions. These matrices are not the same size. Therefore, we just can't add them together. This addition problem is just undefined. We can't do it because we can't match up all the numbers. With D, you would just subtract -1 minus 0, which is -1. -2 minus -7 means -2 plus 7, which is a 5. 0 minus 5 is -5. And then 8 minus -9 means 8 plus 9, which gives me a 17. At the bottom of the page, we talk about an additive inverse. So I just want to make sure that you understand that numbers are additive inverses if you add them together and the answer is 0. So for instance, 5 and -5 are additive inverses because when you add them up, you get 0. Inverses kind of undo each other. So 5 and -5 undo each other if we're talking about addition. We end up with an answer of 0. Now, this 0 here is not actually the number 0. It stands for what we call the 0 matrix. Because now we're talking about matrices that are additive inverses of each other. Well, when you add two matrices together, your answer is another matrix. It's not just a number, right? When you add two matrices together, your answer is another matrix. So if two matrices are additive inverses of each other, when we add them together, we're not just going to get the number 0, we're going to get what we call the zero matrix, which is just a matrix that has a bunch of zeros in it. It's just full of zeros. So let's just use example B here. And I'm thinking, what matrix would I add to this one so that my answer is a 0 matrix? And that 0 matrix would have to be the same dimensions as what I started with here. Well, we know that if we have a 9, we'd need a -9 to get a 0. We start with a -3, we need to add a 3. 2, we need a -2. 8, -8. 1, -1. 8, -8. And so these two matrices are additive inverses, because if you add them together, you get this 0 matrix that's just all zeros. All right, moving on here. So what we have here on this page are some kind of word problems where we're going to use a matrix to represent some kind of information that can just be arranged, right? This is data here that could just be arranged better. So in this case, we're going to dinner and there's 2 pizza places that we could eat at, and it tells us the prices at each place for a pizza and a soda and a salad, and that's at Gina's and at Tony's. And it wants us to display this information in a 3x2 matrix. Now, just to remind you, a 3x2 matrix has 3 rows and 2 columns. So a 3x2 matrix kind of looks like that, 3 rows and 2 columns. So what we need to think is, what do we have 3 of here and what do we have 2 of? Well, what we have 3 of are things we can order: pizza, soda, salad. What we have 2 of are the restaurants, Gina's and Tony's. So I'm going to kind of label this a little bit. 1 row of my matrix is going to be the price of a pizza. 1 row is going to be the price of a 2 liter of soda. And 1 row is going to be the price of a salad. As far as my columns go, 1 column is going to be the price at Gina's, and then the other column is going to be the price at Tony's. And I'm just going to make a matrix out of this. So I can take the prices from Gina's: $12.16 for a pizza, $1.15 for a 2 liter, and $4.05 for a salad. And then go to Tony's. Tony's charges $10.86 for a pizza, and 89 cents for a 2 liter of soda, and $3.89 for a salad. So I've just arranged this information in a way where it makes those numbers a little bit more accessible if we needed to do anything with them. We're not doing anything with them yet. We're just kind of showing how you would arrange them. Now, this next part says that at Gina's, they charge 50 cents for an extra pizza topping, but Tony's only charges 30 cents. It also says that at Tony's, they charge you $1 for salad dressing, which seems like a total ripoff to me. I can't imagine charging $1 for dressing on your salad, but whatever, we'll go with it. So what I want to show here is how we would use matrix addition and how we would set that matrix addition up. So I'm going to recopy that matrix that I had at the top there. And then we're going to add on a matrix that includes these increases in prices. Now remember that if I'm going to add 2 matrices together, they have to have the same number of rows and columns. But really the most important thing in this problem is deciding where we're going to put these new numbers in this new matrix. So it says at Gina's, if you want an extra topping, you're going to add 50 cents. So I need to put that 50 cents in the position that corresponds to the price of a pizza at Gina's, which we know is that upper left position. So I'm going to add that 50 cents to the upper left. Tony's, an extra pizza topping, is 30 cents. So the price of a pizza at Tony's is the upper right number. So I'm going to put that 30 cents in the upper right. Now it tells us that at Tony's, they're going to charge $1 extra for salad. So I need to look up here and see that a price of salad at Tony's is the bottom right number, and so that's where I'm going to put that 1 for the extra dollar for the dressing. We don't have any other increases in price, so I just enter a 0 in those other positions, and now we can very easily add these matrices together. So 12.16 plus 50 cents is 12.66. 10.86 plus 30 cents is 11.16. The second row isn't going to change at all. And then the third row, the 405, stays the same, and we add 3.89, and we add $1 to that, and we get $4.89. So if you add a pizza topping and you get dressing on your salad, which I'm assuming you're going to, now this matrix represents the prices that you're going to pay. And I'm not going to do every example in these notes because I just don't feel like there's a need to, and we didn't do them all in class. But remember, they are all worked out completely in the key to my notes in the chapter 2 folder. Okay, the next thing that we need to learn about matrices is what we call scalar multiplication. And before we can really understand what that is, we need to know what this word scalar means. So the word scalar is very simple. That's just any old number, just a regular number, like 5 is a scalar. -10 is a scalar. These are just regular numbers. And you might be asking, like, well, why didn't we call those scalars before? Well, the reason was because we didn't need to. There wasn't anything else on the table. We just always dealt with scalars. If you took pre-calculus at any point, you had a chapter on vectors. And during that chapter, you talked about vectors and scalars. Vectors are quantities that have magnitude and direction. So, like, you know, I threw the football with a speed of 30 miles an hour in the northwest direction. It has a direction to it. Scalars don't have direction. In this case, we have scalars and we have matrices. So a matrix is not a scalar. A matrix has a lot of scalars inside of it, right? It's made up of a bunch of scalars, but a matrix is not a scalar. See this -2 right here? That -2 is a scalar. So this is a scalar multiplied by a matrix. And I bet you don't even need me to help you with this. Scalar multiplication means we're just going to multiply every single number in this matrix by -2. So -2 times 1 is -2, -2 times 7 is -14, -2 times -3 is 6, -2 times 4 is 8, the next one would be +10, and then -6. Last row, I would get +2, 0, and +16. And so we just multiply every number in the matrix by that scalar. And that's how scalar multiplication works. It's easy. I'm not going to do these word problems at the bottom here because I just don't think, I'm not going to say that they're like useless or whatever, but it's just not worth our time right now. So the last thing that we're going to discuss in this video is the determinant of a matrix. That got cut off there. It's a determinant. You can see that right down there below. And really, it just says a determinant is a special number associated with a matrix. And that's really as much as we need to know about it right now. I'm not going to go into any depth about what a determinant is because honestly, it's a little bit complicated and it's just not something that we need to know right now. So every square matrix has this number that's associated with it, and that number is called a determinant. And we're going to use those determinants to solve some problems later on. So we're going to get use out of it. And it's just kind of a number that we need to be able to find that we're going to use to solve some other problems. We're not going to go into any more depth about really what it is, though. You just need to be able to find it. Now, first of all, you can only find the determinant of a square matrix, meaning it has to have the same number of rows and columns. If the matrix is not a square matrix, then you cannot find the determinant of it. It's that simple. We're only going to be finding the determinant for 2 sizes of matrices, and those are 2 by 2 matrices and 3 by 3 matrices. We're only going to do 2 by 2 and 3 by 3. Now, there's a couple ways that you can see, that you can look at a problem and know that you're supposed to be finding the determinant of it. One way might be that we could give the matrix a name. Like down here, we're calling this matrix matrix A, And then I could say, find the determinant of A, and that'll be DET of A. So that DET tells you you're supposed to find the determinant. Or just in this case, in example 4, I give you 2 matrices and it just says, find the determinant of each one. So there you go, that's easy. The other way you know that you're supposed to find the determinant is if you see these straight lines. You see the difference between the regular square brackets and these straight lines here? The straight lines mean you're supposed to find the determinant. So down here in example 5, you'll see that the directions do not say find the determinant. The directions just say evaluate, but those straight lines mean you're supposed to find the determinant. So it'll either say DET or you'll see those straight lines and that means determinant. All right, so we're going to start with finding the determinant of a 2x2 matrix, and it's real simple. There's a formula right here, but I want you to notice that A times D is really just this diagonal here, and B times C is really just this diagonal here. So when we find a determinant, we're just subtracting these diagonals. So for this first one, we find the determinant by multiplying diagonally. 3 times 6 gives me 18. Then we multiply the other diagonal. 5 times 4 gives me 20. And we simply subtract those, and our determinant is -2. Your determinant is always a scalar number. Okay? You'll always end up with just a scalar, regular old number. With example B, we multiply the first diagonal and we get -7. We multiply the second diagonal and we get -18. Now remember that we're subtracting here. We're always subtracting. So in this case, we're doing -7 minus -18, which means we're actually going to add 18, and our determinant will be 11. Down here, when we have the straight line brackets that mean determinant, we do the exact same thing. 2 times 10 is 20. -5 times -3 is 15. We subtract, and our determinant is 5. For the next one, -2 times 5 is -10. 7 times 3 is 21. We subtract, and our determinant is -31. Awesome. That's all there is to it for 2x2 determinants. You just subtract those diagonal products. All right, then, so for 3x3, you can see that the formula here is a lot more complicated, and oh my gosh, would it be a pain to take whatever number A is and plug that in for all the A's, and then take the B and plug that in wherever you see a B, and so on. What a nightmare. I'm going to show you an easier way to do this formula. We're going to be doing the same thing. We're going to be using this formula. We're just not going to be plugging the numbers in here. This process is described right here, so I'll let you read through that if you ever need to, but I'm just going to describe how it works right now. So this is to find the determinant of a 3x3. And again, I am explaining this process that it's describing right here. Okay, I'm just not going to read through these steps. So the first thing you want to do is take the first 2 columns and recopy those right outside to the right of that matrix. So just the first 2 columns, not the third one, just the first 2 columns, recopy those outside of the matrix. And now we're going to start doing diagonals again. We're going to start in the top left, and we're going to do a diagonal that goes down and to the right. And we're going to multiply the numbers in that diagonal. 1 times 1 times 2 is 2. Then we go on to the second diagonal. So we go over one number, and now we go to the second diagonal, which is 3 times 3 times 4. So that's 9 times 4. That diagonal is 36. And then we go over a number, and we do our next diagonal. 5 times 2 times 5, that's 25 times 2, which would be 50. Okay, that's it for diagonals going that way, because you can see my next diagonal would only have 2 numbers in it. So we're only using the diagonals that consist of 3 numbers. We're going to take these 3 numbers and we're going to add them together. So 2 plus 36 plus 50 adds up to 88. Now we're going to do the same thing, just going the other direction. So we're going to go to the bottom left. We're going to do a diagonal that goes up and to the right. 4 times 1 times 5 is 20. Okay, we go back and go over a number and we do our next diagonal. 5 times 3 times 1, that's 15. And then again, the next diagonal, 2 times 2 times 3, which is 12. We add those numbers together, and 20 plus 15 plus 12 is 47. Okay, remember with 2 by 2s that we did the same thing. We did the diagonal going this way, and then we did the diagonal going that way. We're kind of doing the same thing here. It's just that there's 3 diagonals that go this way and 3 diagonals that go the other way. This last step is going to be the same as before. We're going to take that 88, we're going to take that 47, and we're going to subtract them. So you do your first diagonal total, which was 88, and you subtract your second diagonal, which is 47. It's really easy to get these numbers out of order because you might want to do like the top number minus the bottom. And by the way, you can organize yourself here however you want to. You don't have to do it exactly the same way that I do. Just make sure that you do this top left, bottom right diagonal number first, and then you subtract the bottom left, top right diagonal number. And so here, our determinant is 41. Okay, let's do example B real quick. So I'm going to recopy those first 2 columns, and then I'm going to start doing diagonals. So I start with my top left, diagonal down, -2 times -2 times 1 is +4. Next diagonal is 3 times 3 times -2, which would be -18. Next diagonal, -1 times 4 times 2 would be -8. Add them together, and that's going to be what? -26, -22. Yep. Okay, then we do the diagonals that go the other way. -2 times -2 times -1 would be -4. The next diagonal is 2 times 3 times -2, which would be -12. And then the next diagonal is 1 times 4 times 3, which is +12. Add those together, and we get -4. Final step is to take the -22 and subtract the -4, which gives me a -18 as my determinant. We do need to do this last one because it turns out, well, not weird, but I need to say something about it. Let me get this set up and working here. Okay, recopy the first 2 columns, 1, -1, 3, 2, -2, 2. Start with your diagonals. Top left, bottom right, 1 times -2 times 1 is -2. The next diagonal, 2 times -3 times 3 would be -18. Next diagonal, 3 times -1 times 2 is -6. Add those together, and we get -26. Now let's go the other way, starting in the bottom left. 3 times -2 times 3 is -18. 2 times -3 times 1 is -6. 1 times -1 times 2 is -2. Add those together, and we get, well, look at that. We get -26 again. When we subtract these numbers, you can see that we're going to get 0. And for now, that's no big deal. The determinant is 0. Fine. The determinant is 0. In a little bit, that's actually going to be a meaningful result to us. Like, that's going to matter that we got 0. That's kind of going to be a special case later on. What I need you to know right now is that this matrix has a special name, and we say that this is a singular matrix. The reason that this is a singular matrix is because its determinant is 0. And again, for now, that doesn't mean a whole lot to us. It just has a determinant of 0. It's a singular matrix. We'll see later on what that means. And it's going to be when we're finding multiplicative inverse matrices. And that if a matrix is singular, that just means you can't find the multiplicative inverse of it. I got some hair stuff going on there. Okay. Ooh, made it even worse. Whatever. So that was kind of the end of day one. It was actually a little bit of the previous day as well, which is why it was a little bit longer. So I'm going to stop it there. That's the end of the first day, and I will see you in the next one, but hopefully I'll see you back in class real soon. All right, take care. See you then.